Okay, so tonight's class, we're basically going to look at some of the formulas which are used under rotation of axis, and later on we'll continue looking at how to use those same formulas. So when we're rotating an axis, here's what you need to keep in mind. So if we use y for the original axis, so here we have the original x-axis, so the original y, I mean, so I'll use small letter y, and here let's have the original x-axis, small letter x. Now let's say that the x-axis is rotated through an angle, and let's say this is rotated through, let's not rotate the original, so just copy this, and we are going to rotate it through some angle. Now, for practice sake, I'll maintain, let's say a 30-degree angle, but it's basically just any angle really, because this is going to be the general, we're deriving the general formula. And let's say the y-axis is also rotated through some angle, the same angle. So since I rotated that through 30, this is starting from 90, I'll go through 30 as well. So this is what we have. Now the concept is that when the x-axis is rotating through the angle here, so we'll just generalize it here and say that the x-axis here is rotating through an angle theta. When this happens, even the y-axis here will rotate through the same angle theta. But we want to look at this part, we just focus on what is happening this side. Now, let's pick a point that is general. Let's pick a point that is located, let's say, somewhere here. We can label this point to be P. You see, this point can be described in terms of the blue axis, and it can also be described in terms of the white axis. The blue axis has the x-axis as capital X. Let's say capital X-axis, and this is capital Y-axis. And in the same way, let me say this is X-axis, and this is Y-axis. So the first part we have already looked at. So I think I've drawn this graph before. So hope you guys are keeping tabs. So we're describing a point P that is somewhere there, and we're saying to find this, its displacement from the origin can be seen as a line that starts from here and it goes all the way up to where this point is. We draw that better. So we're coming up to there. So that line can be seen to have a magnitude R. So that is from O to where the point P is. Now, we can describe P in terms of the blue axis and the white axis. Let's start with the blue axis. So if we look at the blue axis, we can look at that point to say, let me go green for this. We can say it will have an x-axis, x component that will be somewhere here. So this will be x, capital X. And it will have a y component that will be here, capital Y. Now, let's say the angle of rotation, or the angle between the rotated x-axis and the line R here, let's take this angle this side, and let's take this angle to be alpha. So I hope you guys are following exactly how I am working out this. So let's take that angle there to be alpha. So here's what you should see. If I just focus on that blue axis, what you should observe, or what you should be able to see from that line, from that graph, is that we have something like this, and then the point R is here, the point P is there, and then the line R is here. So if we just focus on the same rotated axis, we are creating a right-angled triangle here, where this is capital X, and coming this side, this is where we have capital Y, and this is a right-angled triangle. And this is where R is. So the angle here, this is the angle I highlighted as alpha. So I hope you guys are able to see it from here. So this is what I have isolated there. Based on that, we are saying that the distance from here to the origin is X, and the distance from here to this part is Y. Because of that, we can easily say that if we use sine alpha, remember sine by SOHCAHTOA, sine is opposite over hypotenuse. The opposite will be capital Y, the hypotenuse will be R. From here, we have Y is equal to R sine alpha. So hold on to this, we'll need it later. In the same way, when we use cosine, we know to say cos theta, or cos alpha, I mean, will be adjacent. The adjacent is X over the hypotenuse, which is still R. When we cross multiply, we see that X, capital X, will be equal to R cos alpha. So we'll hold on to this as well. We will need it. Having done this, we are now done dealing with the rotated axis. Now we want to look at the same point, but now we want to see it from the original axis. So now I don't want to look at that green notation. Let's go to a different color. I've used yellow already. Okay, yellow, yes, has been used. Let's go something that will be visible enough. Let's go red. So we know to say in the original axis, we will have this. This is where we'll have small x, and we will have this. This is where we'll have small y. So if I was to now sketch it so that you guys can picture it, we have the original y-axis, we have the original x-axis, and our point P is somewhere here. You still have the line from the origin to the point P, still the same R, but now we are creating this triangle, where this line here is small x, the base here, and the vertical one here is capital small y. So this is at small y here. The angle between R and the horizontal, can you guys guess what that angle is between R and the horizontal? Can you see it? What's the angle between the x-axis and the line R? You have to observe that the angle there will have to run from R all the way up to that white horizontal line. And that will be a combination of the angle alpha and the angle theta. So when I'm using cos the angle, it has to be, this angle here is alpha plus theta. So when I'm using SOHCAHTOA in this case, I will have to be saying sine alpha plus theta, because that's the angle I'll be saying it is opposite to y. So it will be equal to opposite over hypotenuse. But notice that in this case, still the hypotenuse is still R. And if I cross multiply, we see that now we can say that this reduces to R sine alpha plus theta being equals to y. So this is where we are now. Any questions so far? So this reduces to y is equals to R sine alpha plus theta. In the same way, so I'll hold on to this. In the same way, if we use cos alpha plus theta, remember cos is adjacent over hypotenuse, The adjacent in this case is x. So this will be equal to x over the hypotenuse, which is r. So when you cross multiply here, you end up with x being equals to r cos alpha plus theta. So this is where we are now. Now, when you reach this point, you will now have to remember the double angle identities. So I'll get this expression and the one for y. So these are the expressions where I want to use the double angle identities. So let's start with the one for x. So if we start with the one for x, we have x is equals to r cos alpha plus theta. But what do we remember from the double angle identities? We know to say the double angle identity for cos is if you have cos A plus B, then you know to say the identity goes on to say you are going to have cos A, cos B, and the sign between has to be a minus. So this is going to be minus now sine A, sine B. So this is the double angle identity for cos A plus B. So now instead of A, we have alpha. Instead of B, we have theta. And correctly, or as the identity is, you have a plus between. So no funny business. So when we use that identity, we now have x is equals to r. I'll put the brackets because all this is multiplying the r here. So cos alpha plus cos theta, not cos alpha plus b, it's cos alpha plus theta. And then minus sine A is alpha, then sine B, and B is theta. So this is where we are now. Notice that this reduces to just r, cos alpha, cos theta, minus r, sine alpha, sine theta. So this is where we are. Now, the final piece of the puzzle involves you recall or to remember what we isolated first. Here, capital Y was identified to be r sine alpha, and capital X is r cos alpha, meaning when you come to this part now, you just have to remember that, okay, if I have r cos alpha is capital X. R sine alpha is capital Y. Again, remember this. We did this earlier. Capital Y is r sine alpha. Capital X is r cos alpha. Meaning that now this reduces to just x is equal to, where we have r cos alpha, this will be capital X. Minus where we have r sine alpha, this will be capital Y. So this becomes the expression that relates the x coordinate to the rotated x and y coordinates when an axis rotates or is rotated through an angle theta. Any questions here? Are we okay?
Hello. Just a little scroll up. I was writing some notes.
Okay.
Just there.
Regan, are we okay? No, great. Kondwani?
Now back down, please.
Okay, Kondwani, are we okay as well? So as I mentioned in our other class, it's rare that they will ask you guys to show these formulas. It's possible. I'm not saying that they can't. It's possible, but it's rare. But now that we're looking at them, if they did ask you, because I came late, but I'm following great. But if they did ask you, this is how you approach them. So we have found the expression for x. Now we want to get the expression for y. And to find it, we will start from here. We did end up with this expression where y is equals to r sine alpha plus theta. So we'll just pick it up from there. And in the same way, we use the double angle identity for sine. So all you have to remember is the identity. You have to recall that sine A plus B is equal to sine A cos B plus sine B cos A. So this is the double angle identity for sine. So knowing or having seen the identity for sine, we can now use the identity. So if we try to use the identity, we're now saying y will be equal to r, open bracket, sine alpha plus theta. This becomes sine A is alpha, and then cos B, so this will be cos, but B is theta, plus sine B is theta, then cos A is alpha. I'll distribute the r, so this is r, sine alpha, cos theta, plus r again, but I'll start with the cos alpha, and then sine theta. So the same way, just like before, we have to remember that x is equals to r cos theta, not theta, alpha, and y is equals to r sine alpha. When we make the substitution, we see that small y will be equal to, where we have r sine, this becomes y cos theta. And where we have r cos, that becomes capital X. So when we rewrite this, this is what becomes x sine theta plus y cos theta. So again, this is how you come up with this relation. So again, we did write this relation in our previous class. We just didn't show how to get to it. Now we have seen how to get to it. Any questions here?
And they scroll up a bit again, please. Yeah, just that's fine.
Okay, great. Okay, now the next that we want to see is another key formula that is used under rotation of axis for conic sections. We did point out to say that if you have a conic section whose general formula looks like this, if you have a conic section which has the cross product, the first thing that you'd have to do is eliminate the cross product. And among the steps for eliminating the cross product, you'd have to find the angle theta. So that is what we were describing in the other class. But now we want to see where the key formula that is used to find the angle theta comes from. We say that to find the angle theta, you'd have to use a formula cot 2 theta is equal to, this was A minus C over B. Here, of course, B must not, we're taking it that B itself is not equals to 0. This is the key formula that we use to find theta. So again, this is a conic section where A, B, C, D, E, and F are known values, and they are real numbers. And then you can easily use them to figure out what this angle theta is. So this is the angle of rotation. So it will not be given to you in such cases. They expect that you know this formula, and hence you can use it. Now, the question that was phrased in that class was, where is this formula coming from? So this is what we want to see. Where is the formula coming from before we move on to see how the formula is used? Is that okay?
That's okay.
Great. Now, the math for where the formula comes from is a little bit long. You see, it's actually a general step to say that, okay, let's say you have a conic section which actually takes this setup. We want to eliminate the cross product. The steps for eliminating the cross product involve substituting for small x everywhere and also for small y everywhere. Now, what are we substituting? We're substituting the formulas we're just from deriving. To eliminate the cross product, you more like have to rotate the coordinate axis so that the cross product disappears. I think I did touch on that in yesterday's class. So we have to substitute x. Wherever we have small x, we're going to substitute x, and this is going to be cos theta minus y sine theta. So we're going to substitute this whole lot everywhere where we have x. That involves here, here, and there. And then everywhere where we have a y, we're going to put x sine theta. And this is going to be plus y cos theta. Notice that we are substituting the formulas we're just from deriving, this one in blue and this one here in blue. So we are just rotating our coordinate axis. Remember, this is necessitated by the fact that, okay, if our coordinate axis were to maintain its form, something like this, a conic section that will have the cross product is, for example, a conic section like this. So if we wanted to eliminate the cross product, it then becomes necessary to rotate the x-axis through an angle theta so that the x-axis now goes like that. And the y-axis has to rotate through the same angle so that it goes more like that. Now, if we were to rewrite the conic section using a rotated xy coordinate system, now we will observe that the conic section will not have the rotated, it will not have the cross product. So what we're doing when we are substituting x and y into this equation, it's like we want to see how this equation or this conic section will look like in a rotated frame. So basically, that's what we want to see. We want to see how this conic section looks like in the frame capital X, capital Y. Instead of small x, small y, we want to look at it in terms of capital X, capital Y. I hope you've got that. So to do that, first step, since this is a generalized formula we need, we will keep it general with A, B, C, D, E, F as unknowns, so that now where we have x, we'll put capital X cos theta minus capital Y sine theta. But remember that x, the first x there is squared. Plus, now I have b. And for b, b has x and y multiplying. So where we have small x, we'll put this. And where we have small y, we will put x. So all this is just bxy. And all this is just ax squared. Have you followed? Are we okay so far?
Just trying to write down this, but following.
Okay. Okay. So I've just substituted for the first two terms. I have to do the same thing for all the other terms. Only these two will have. F doesn't have x or y. So only those two have. So let's move on to cy. So I'll say plus cy squared there. So where there is y, so that's small y, I'm going with x sine theta plus y cos theta. And again, remember that is squared. Then I have plus, now I'm going to d. And what we have for d, d has an x. So it's going to be d multiplying. So where we have small x, we are substituting x cos theta minus y sine theta. So that is d. Then we have e. E comes with y, so I'll say plus e. And then where we have y, we'll put x sine theta plus y cos theta. And the last one is f. It doesn't have an x or a y, so just going to be plus f is equals to 0. Now, what you have to do is you have to simplify this, square it, multiply this, distribute, expand I mean, square this as well, and then also simplify this. The goal here is you want to come and isolate everything that has an x, that has a y, that has an x squared, that has a y squared. You want to come and group them together. So let's go term by term. I'll change color here. So let me start with the first term. I'll do it in yellow so that it's easy to track it. So we'll have a here. When I square this, it's x cos theta squared. It will be x squared cos squared theta. And this is going to be minus. So x and y will multiply, but it will do it twice. So it will be 2x y. And this is going to be sine theta cos theta. Please, you have to follow through this and keep double checking what I'm doing so that I don't make a mistake. There's so many things involved here. It's easy for me to make a mistake as I try to skip some steps here. Okay, and the last part will have to be this multiplying itself, which will make it positive, and it will be y squared, and then sine squared. So if at any point I write something that you're not very clear of, feel free to ask that I explain why it comes out like that, so that I also use that to make sure that I don't have a mistake. Regan, power keeps cutting here. Ready power is gone and my phone is low. Oh, okay.
Question, please.
Go ahead.
So I've noticed the square in the expansion, you're putting it between sine and theta. Why isn't it outside the theta?
Oh, okay. So the tricky part there is that if I give you have to actually see that this is what happens every time in math. If you have sine 30 squared, when the square is not with, you can write it like this with the brackets. It's easy. You know it's sine 30 and sine 30 is 0.5. You know to say this is 0.5 squared. You easily get the correct answer. The problem is if you just brought the square inside and wrote it as sine 30 with the square here, you have to see that the confusion here is that you can easily square the 30. If you actually tried on your calculator to say 30 squared, which would just be 9 here, and then with 2 zeros, if you did this to say sine 900, notice that this is not the same as this. It'll give you a wrong thing. It'll give you something else. Instead, the correct representation here is to write it as sine, and then the square comes here, and the 30 comes here. The idea here is that what is being squared is not the 30, but it is the sine itself. So sine 30 is what is being squared. You get why we write it there.
I get it. Thank you.
Great. Okay. So this is the first term there. Let's go to the second term, the one coming with a b. Let's do it in yellow. So I have to expand this entire lot there. So let's pick up plus, that's b. When expanding this, now what you have to see is this term here, this is a difference of two squares. You have to see, this is what helps us eliminate the cross product, because that is a difference of two squares. A difference of two squares will always have a specific way it simplifies. It will always give you an expression, which will be the first term squared minus the second term squared. That is how a difference of two squares will always simplify. But if you're not sure about that, let's do it step by step for now. So the x cos theta will multiply the x sine theta, which will give you x squared. So x cos multiplies x sine, and then this will be sine theta, and then cos theta. Next, I'll say the x cos multiplies y cos. So this will be plus x, y. So it's cos cos. So this is going to be cos squared, because it's cos multiplying cos, x multiplying y. Now I'll come with a minus sine, minus y sine. Minus y sine multiplies x sine, which gives us minus x, y, but it's sine multiplying sine, so this would be sine squared theta. Next, minus y sine multiplies plus y cos. So it's y, which gives us minus y squared. Now this is sine and cos, which gives us sine cos. So the expansion is now complete. Now look at what happens. See the middle part. Okay, let me just double check my work. It looks like we're okay. So let's just simplify this term. Here, of course, a little bit weird, but still simplifies. Notice that when we simplify this part here, how will it simplify? Let's see. So we do have xy, but this is sine, and that is cos. So basically, those are all going to survive there. So you can keep it like this. I thought one part was going to subtract out because of the difference of two squares, but it wasn't really difference of two squares because this term and this term are different. So this is not really difference of two squares. Okay, so let's proceed. Let's just distribute that b. So I'll just delete some so I save a little bit of space here. So I'll distribute the b there. And if I distribute, okay, the other one I didn't distribute, so perhaps I should just leave it like that. Okay, so that sorts out the one in green. Now let's come to this third term. For the third term, let's go blue. For the third term, we are now expanding this. That's c, open bracket. So I am just going to square there. So it's x sine. So if that is squared, it will be x squared and then sine squared. And then we have, they will multiply each other. So it will be this times that and then the likes. So it will be done twice. So it will be 2x, y. And then it will be sine and cos. And finally, it will be this last term there squared. So it will be y squared. And then that is cos squared. Okay, that sorts out the term with a C. Now we go to the term with a D. And let's choose a weird color. For that one, we're just distributing that D there. So it's going to be plus D, and D will multiply X cos theta minus D Y sin theta. And this one here also is straightforward. So you can just distribute that E. So it will be E X sin theta, and then plus E Y cos theta plus f is equals to 0. This term here in this weird color will not really affect what we're doing much. The trick will be with what is coming up on top there. You'll see the term that will actually be very important. So I'll distribute the A. What I want to do now is I want to isolate everything that has an x squared, everything that has a y squared, everything that has the cross product. Notice that the new cross product now is this xy here. Do we have, again, we have it here. We also have it here, and that's all. So, and we also have it here. Yes. So those will actually be the key terms that will actually help us identify or come up with a formula that we want to do, that we want to find. But for now, let's distribute. From the expression in yellow, when I distribute A, I have A x squared cos squared theta minus 2A, here there's 2A x y sine theta cos theta. Let's move this down a little. And then we'll have plus, and then the A again, A, and that is y squared sine squared theta. And then we'll have plus. Now I'll send the B inside. B, that will be x squared sine theta cos theta. And here again, B joins xy, and that is cos squared theta minus. Now we have B joins here, bxy sine squared theta. And we have minus by squared. That's minus. I think that was sine theta cos theta. Just verify that. That is here, y squared, sine squared, and then we have cos squared. Not sine squared, sine theta cos theta. Then we come to this one down here. C also goes inside, plus C, and that will be x squared sine squared theta, and then plus 2C. Then we have, where is that? Yeah, that's that term, that's the cross product. Let me write it properly. To C, xy, that's this term, sine theta cos theta. And then we have the last term there, which is C y squared, and that will be cos squared theta. And of course, this remains exactly as it is. There is nothing to simplify there. So it will be plus all this. And that will be equals to 0. Okay. Now, having done this, now you want to group everything with an x squared, everything with a y squared, and everything with the cross product. Those will be the key terms. You can actually rearrange this. Just make sure you group the like terms. So this has an x squared. This has an x squared. This has an x squared. And that's all. So we'll write all those together. So, and I'll factor out that x squared. I'll go red since this is the final thing. So this is A cos squared theta. I'm factoring out the x squared itself. So I've just written a cos squared theta. Now come to this term. So that term has b sine theta cos theta, and it's positive. And then next, so this is sorted out. Next, it's this. That's c sine squared theta. And the x squared comes outside. So this is what we have with the x squared. Next, I'll go to the terms with the cross product. So the terms with the cross product, let's find them. This term has a cross product. We have a cross product here. We have a cross product here. We also have it here. We also have it here. I think that was the last one. So we have 1, 2, 3, 4 terms with the cross product. Okay, let's get those. The first one is 2a sine theta cos theta, and that's positive. Minus, I mean. This is minus. So, but I'll just write plus, so the minus will be here, minus 2a. Then sine theta cos theta. Again, I'm factoring out the xy. That's the first term, which is this. Next, b, and then cos squared theta. That is positive. Yes, that is positive. B cos squared theta. Next, this term here. This is minus b sine squared theta. And the last one, so that is sorted out. This is sorted out. The last one is this one here, which is 2c sine theta cos theta positive. So that is the last one. Okay, so let's put in brackets, and this we factored out xy. Okay, we can go on to write all the other terms. You need to do, the next one you will need to do is the one for y, and the one for y squared, I mean, you have this term has a y squared, this term has a y squared, and this term has a y squared. So that is all. And then after you're done with the one with the y, notice that you've sorted out everything here in white. So you just have to finish writing this at the end. But the key thing that you actually need to get the answer, in other words, this actually continues until the end. But to eliminate the cross product, notice that with our rotated system, this is our cross product here. So if when we rotate through that angle theta, we have eliminated the cross product, it means that by doing the rotation that we have done, this term here must reduce to 0 so that the term xy here actually disappears. What does that mean? It means that the angle theta that has to be placed here has to be an angle which ensures that this highlighted in blue, the term, the coefficient of the xy, reduces to 0. This is where the trick lies. Once you observe that trick, all you have to do now is equate this coefficient of the xy to 0, and then simplify what you have, because it's the only way that the cross product disappears from the rotated expression. So you have plus b squared, b cos squared theta, minus b sine squared theta, b sine squared theta, and then plus 2c sine theta cos theta. This has to be equals to 0 if the cross product has to become 0. Have it in there. Okay, so any questions on that? Have you guys understood why I am equating this to 0? Have you got it?
Because we have to eliminate the cross product.
Yes.
In this case, is the xy.
Yes. So the cross product has to be 0. So for the cross product to be 0, it means that the coefficient of the xy must be 0. This is the reason why we have equated this to 0. So having done that, all we now need to do is just simplify this. Okay, kindly mute yourself. Okay, so we now just need to simplify this expression. And there are various ways that you can do this. Let's see, some things here seem to be to have things in common. So we now just want to simplify this. For example, we have the sine theta here. So these can be grouped together. And we can write them as 2c sine theta cos theta minus 2a sine theta cos theta. So by writing this, then these two can follow up on their own. So these will be plus b cos squared theta minus b sine squared theta is equals to 0. From these two, you can actually observe that they have 2 in common, and then the only difference will be c minus a, because they also have sine theta and cos theta in common. And then these two also have that b in common. So you can also make that observation. Have you seen that? So if you actually observe that b here is common, you can end up saying that, okay, you can write this as b, and this is going to be cos squared theta minus sine squared theta is equals to 0. At this point, we are almost there. So we are almost there. You just need to keep in mind your trig identities here. Can you identify what this is? Do you know the identity that gives you this? For this one, you have to remember the double angle identity for cos. Remember I said if you have cos A plus B, this becomes cos A, cos B, minus sine A, sine B. But imagine if A was equals to B, meaning that now you have cos 2A. Notice that this will now be cos A, but cos A is just cos squared A, minus sine A, which will also just be sine squared A. So this is the identity that we are going to use here, because we see this is cos squared theta minus sine squared theta. This implies that this is the same as just cos 2 theta. Do you agree? Do you agree with that?
Yes.
Okay. So based on that, I'll just copy the rest of this. But in place of this whole lot, this part, I'll just put cos 2 theta is equals to 0. So this is where we are now. We're almost shaping up if you just try to observe this. So we are almost reaching the end of the derivation. So keep in mind of where you're going. You're going towards cot 2 theta being equal to A minus C over B. This is where we're trying to go. This is the final solution we want to see. Notice that we have already obtained the B. We have already seen cos 2 theta. So we are almost there. All we need is sine 2 theta. But can you see where sine 2 theta will come from? Don't you see what this is here? So here, you'd have to observe this. And using the double angle identity for sine A plus B, if you recall, we had sine A, sine B plus sine B cos A. But in an event that A is equals to B, what this becomes is sine A plus A, which is just sine 2A. This reduces to sine A. I wrote sine here as well, sorry. This is cos. So this reduces to sine A cos A plus sine A cos A as well. Meaning that since this is the same as this, they'll add up to 2 sine A cos A. So if you look at what we have here, we have sine A cos A, and we have a 2 here. So if I was just to write the 2, instead of writing it here, if I just put it here, you have to see that this entire lot here is actually the same as just sine 2 theta. Do you agree?
That's a little behind there.
Where?
Okay, so the first cos 2 theta, I think it's from that stage where I think I lost you.
So it was here.
Yeah, I lost you from there.
Okay. So the observation here was you having to recall that this is the same as cos 2 theta. So what I did was I just derived the identity so that you can easily relate to it. If you have cos A plus B by double angle identity, this is what you will have. But if the angles were the same, if A and B were the same, so if A is equal to B, it means that you have A plus B. A plus A means it's the same. And A plus A is 2A, meaning that our cos A plus B uses to just cos 2A. So since this is cos A and this is also cos A, it becomes cos squared A. Have you seen that?
Yes, please. Hold on there. Try some.
Okay. So don't be stressed about writing. I can easily send this document to you once we are done. The key thing is to understand how we're doing this.
Okay.
So in the same way, since A here is the same as B, so I can easily just write A where we have B there. It becomes sine A, sine A. So again, this reduces to just sine squared A. Have you seen that?
Yes.
Yeah. So if our angle is instead theta, it now means that cos squared theta minus sine squared theta by that identity can be replaced by cos 2 theta. Have you seen that?
Okay, I will stay there.
Okay. So what I did then was I then came to this part. So where we had cos squared theta minus sine squared theta, I replaced with just cos 2 theta using that identity. Now, what I did was the left part of the expression was this, or the first part of the expression, it was this. It had the two was somewhere here, but I just put it here for clarity, what is coming next. Doesn't matter the position of the two, since all this is multiplying. But then I also say that, okay, the double angle identity for sine says this. It says that if you have sine A plus B, it would be equal to sine A cos B plus sine B cos A. In the same way, if A and B were the same, meaning that this is now A plus A, which is 2A, the identity reduces to sine 2A being equal to sine A cos A. In the same way here, it will be sine A cos A. But because these two terms now are the same terms, because the angle is the same, they can now add up to just 2 sine A cos A. Are we together?
No, I'm a bit lost.
Where?
That are just the sine A plus is equals sine equals C plus sine B plus C. How is it different?
Okay. So, do you know this identity? Do you know it? Now, let's say A is equal to B, and let's say both A and B are equal to an angle theta. So what is A? I will put theta. Where there is B, I will also put theta. Theta plus theta can now be seen as just 2 theta. Are you okay with this part?
Yes, yes.
Now we will have sine theta cos theta, because where is A, I'm putting theta, where is B, I'm also putting theta. Then plus sine B, again, where this B is a theta, then cos A, again, that's a theta. Don't you see this whole thing is the same as this whole thing?
Yeah.
So they will add up, it's the same as x plus x, which will give us 2 times the same term. Do you agree now?
Yes, it's the same.
Okay. So this is the identity that we're going to use. We just observed that sine 2 theta is actually equal to 2 sine theta cos theta. So when it comes to our expression here, when you get this expression, we have just seen one thing. This term here, this is actually just the same as what? It's the same as just sine 2 theta. So in place of that, you can actually just have sine 2 theta. So in place of this, we'll have sine 2 theta. Then plus this will be b, this will be cos 2 theta. That is equal to 0. You see that?
Yes.
Okay. Now, one of these terms can go to the right-hand side, depending on the one that you want. I will take this term to the right, so that now I will have b cos 2 theta is equal to negative, and this will be c minus a, then sine 2 theta. When I divide both sides by sine 2 theta, this cancels. Now I will have b, and this will be cos 2 theta sine 2 theta equal to negative c minus a. Do you see that?
Yes.
So now we have b cos 2 theta over sine 2 theta equal to, distribute the negative inside, which is negative c plus a. So upon reaching this part, we have actually found the answer. Firstly, what is cos over sine?
Is it cot?
Yes, cot. Cos 2 theta over sine 2 theta is equal to cot 2 theta. Meaning that we now have B cot 2 theta is equal to, on the right, I can start by writing the positive A there. So this will be A minus C. Divide both sides by the B, and then we have the expression we're looking for, which is A minus C of B. This is what we're going for. Okay, any questions?